Hello students, in this video lecture we are going to see the analysis of indeterminate truss by flexibility matrix method. So let us see the example. Analyze the truss in figure by flexibility matrix method and find all the bar forces. Assume the top chord members 1, 2, 3 to have twice area of cross section of the other bars which have the same section. So this is our indeterminate truss. So it has two supports. At support A, both the supports are pinned. Okay. So it is our truss. The solution, first and foremost thing in the flexibility matrix method is, so first thing, so we should determine the degree of static indeterminacy of the structure or redundancy of the structure, and also choose the redundant. So we already know, so degree of static indeterminacy is equal to external indeterminacy plus internal indeterminacy. So external indeterminacy is equal to number of unknown reactions minus number of available equilibrium equation. Then internal indeterminacy, it depends upon member configuration. For truss, for two dimensional plane truss, so internal indeterminacy is equal to m minus 2j minus 3. So first, so let us see how many reactions are developed in a structure, in a truss structure. So it has only two supports. Both the supports have two reactions, one vertical reaction, then another one is horizontal reaction. So totally 4 unknown reactions. So number of unknown reaction R is equal to 4, HA, VA, VD and HD. Number of available equilibrium equations is equal to 3. For two dimensional system, it is equal to 3. So which is equal to summation of H equals 0, summation of V equals 0, then summation of M equals 0. Then the external indeterminacy is equal to, external indeterminacy DSE is equal to number of unknown reactions, DSE is equal to number of unknown reactions 4, number of available equilibrium equation 3. So the external indeterminacy is equal to 1. Then internal indeterminacy, it depends upon number, depends on configuration. So it depends upon number of members and joint. So there are 10 members in a structure. Okay. So there are 10 members. So number of joints is joints 1, 2, 3, 4, 5 and 6 joints. So number of members 10, number of joints or 6. So the internal indeterminacy ds psi is equal to m minus 2j minus 3. So number of members 10 minus 2 into 6 minus 3. So 12, 2 6 are 12, minus 3 9, 10 minus 9 1. So internal indeterminacy of the structure is equal to 1. So total indeterminacy is equal to external plus internal. So total indeterminacy, external is 1 and internal also 1. So totally 2 degree of indeterminacy. So in other way, we can get the indeterminacy, total indeterminacy is equal to m plus r minus 2j. So m, so totally 10 members, are reactions 4 reactions. So there are 6 joints. So from that degree of indeterminacy 2. So this formula gives the total indeterminacy. But the first one, the former one gives a separate what is external, how many external indeterminacy are available, then also shows the number of internal indeterminacy. So the truss is statically indeterminate both externally and internally with the degree of indeterminacy 2. Choose the bar force and member 10 and horizontal reaction HD as 2 redundants. Now we are going to select the redundants. So in this case there are 2 redundants. So we choose force in member 10 and horizontal reaction HD as 2 redundant. So one is from external A. So out of 4 external reaction, so select one as a redundant. Then out of 10 member force, you can also select one redundant from this member force. So one from external, another one from internal. Okay. Then second step is remove the redundant and assign one coordinates in the direction of each redundant. So first redundant is internal redundant, that is we removed F10 force and assign coordinate 1 for F10. Then Second result is the HD reaction. Remove that HD reaction, now it becomes a roller supporter. Apply a assign a coordinate 2 for HD. Okay. Then develop flexibility matrix. By unit load approach, the element of the flexibility matrix Fij equal to Fji is equal to summation of Si Sj into L divided by Ae, where Si is equal to force in member due to unit load at coordinate I. Si is equal to force in member due to unit load at coordinate I. Sj is equal to force in member due to unit load at coordinate j, where L by Ei is equal to axial flexibility of a member. The summation covers all the members of the truss. Okay, all the members of the truss. So now we should make a table like this. Okay, so first one is member, then length, then Ae, then L by Ae, S1, S2, S1 square, S2 square, S1, S2. So what is S1? So S1 is the force in members due to unit load applied at the coordinate 1, where S2 is equal to force in a member due to unit load applied at the second coordinate. Okay. So first we are going to determine the value of S1. So for this we should apply unit load at coordinate direction 1 only. Okay. So this is our primary structure. After removal of redundant, it becomes a determinate structure, that is called as a basic determinate structure or primary structures. Now apply unit load. Along F. So now apply unit load along first coordinate. Then determine the support reactions with the help of equilibrium equation. Summation of moment about A equal to 0, so which gives Vd is equal to 0. Then summation of V equal to 0, which gives Va equal to 0. Then summation of H equal to 0, which gives Ha is equal to 0. Okay. So now apply equilibrium equation. The first equilibrium equation is summation of Ma equal to 0. So apply equilibrium equation about A is equal to 0. So there are two forces at E and C. Now resolve this force, one kilonewton force into horizontal and vertical component. The horizontal component, that is horizontal component is 1 cos theta, vertical component is 1 sin theta. Then taking moment about A is equal to 0, finally Vd is equal to 0. Then apply vertical equilibrium equation. So there are 4 vertical forces, Va, Vd, then 1 sin theta upward, 1 sin theta downward. Okay, finally V is equal to 0. Then apply equilibrium equation, Ha is equal to 0. Then determine the member force for all the 10 members, all the 9 members. So out of 10 members, 1 member is taken as relative. So we should determine the member force for all the 10 members. Okay. So take each joints. First let us consider joint A. Okay. So this is our joint A. So joint have totally 4 force. So one is Va, so which is equal to 0, then Ha also equal to 0, then it is connected by 2 members. So one is AE member initially taken as tension, then FAE, then FAB, then this angle is theta. This angle is already known. Okay. So now apply equilibrium equation, summation of H equals 0 and summation of V equals 0 for this joint. So from applying this equilibrium equation, we found FA is equal to 0, FAB also 0. Then consider joint D. Joint D have totally 3 forces. Okay, one vertical reaction Vd which is equal to 0, then FDF force, then FDC force. Now apply equilibrium equation for this joint, summation of h equals 0 and summation of v equals 0. So from that equilibrium equation we found theta is equal to member force is equal to 0. Then consider joint E. So joint E, at joint E there are 4 members. Okay. So one is FAE, so which is already known, this is 0. Then FEF is unknown. Then vertical one is FEB, this is unknown. Then FEC, that is 1. That is one external force, one unit force is applied along F10 member direction, that is EC direction. Then apply equilibrium equation. Then finally we found member force is equal to 0.6 for EF, member EF has compressive force of 0.6. Then EB also have also in compression, its magnitude is 0.8. Then likewise continue joint F, then determine the member force of each and every member, then write it down in this table. So first member 1, the length of the member 1 is 5 meter. Then axial rigidity AE of the member, only top cut has twice area of cross section, other two members have 1 times area of cross section. So 1, 2, 3 are the top chord members. So length of first member is 5, then axial rigidity is equal to 2 times AE, then L by A is equal to 5 by 2 AE. So likewise write all these things. So for all the 10 members, first thing we should write the length of each and every member, then write axial rigidity AE, then L by A value, then S1 value we found, then S2 value. So S2 value is determined by, so apply unit load at the coordinate direction 2. Okay. For in the primary structure we should apply unit force along second coordinate. Okay. So after applying this unit force, now determine the support reactions. Okay. So this support reaction is determined by applying equilibrium equation, summation of MA is equal to 0, summation of V equals 0 and summation of H equals 0. So from that equilibrium equation we found VD is equal to 0, VA is equal to 0, then HA is equal to 1. Now take each and every joint, then apply equilibrium equation. Now draw the free body diagram for each and every joint, then apply equilibrium equation. After that you should determine the member force of each member. Okay. So finally we determine the member force for bottom cut as 1 kilonewton compression, all other members have 0 stress, 0 force, carries 0 force. That is also written in this table. Write S2 value for all the 10 members. Then S1 square. So square the S1 value, write it down. Then S2 square, then S1 S2, multiplication of S1 S2 value. Then finally the element of the flexibility matrix, F11 is equal, we know the general formula, Fij is equal to summation of Si Sj into L by Ae. Okay. So F11, for f of F11 I and j both are equal to 1. So therefore summation of S1 L by Ae. So that is written as S1 square L by Ae. So substitute for all the members, then add it. So finally F11 is equal to 16.74 by Ae. Then F12 is equal to, F22 is equal to summation of S2 square L by Ae. Take summation of all S2 square L by Ae term. Then F22 is equal to 9 by Ae. Then F12 equal to F21 is equal to summation of S1 S2 L by AE. Substitute all the values, then finally F12 F21 is equal to 1.8 by AE. Then finally the flexibility matrix is a 2 by 2 square matrix. Why it is? Because it is a we selected only two coordinates, only two redundancies, therefore it is a 2 by 2 square matrix. So flexibility matrix is equal to 16.74 by AE, 1.8 by AE, 1.8 by AE, 9 by AE. Then now remove the redundant and find the displacement in the direction of assigned coordinates due to given loading. Now we are going to determine the displacement of your primary structures in the assigned coordinates. So that for this also we apply unit load approach. So deflection delta 1L is equal to capital S small s1 L by AE, delta 2L is equal to summation of capital S small s2 L by AE, where capital S is equal to force in member due to given system of loading, given external loading. S1 is equal to force in a member due to unit load at coordinate 1 only. Then S2 is equal to force in a member due to unit load at coordinate 2 only. Then L by E is equal to axial flexibility of your member. So this is our structure. Now remove the redundants. So we remove the HD and F10 member. We taken HD and F10 as two redundant. Now remove these two. It becomes a primary structures. Okay, so primary structure with given loadings. There are two loads. So two are 40 kN load at joint E, and then 40 kN load at joint F. Okay. First, so again we should make a table like this. Okay, so member length AE, L by AE, yes, member force due to external loading, S1, member force due to unit load applied at coordinate 1, member force due to unit force applied at coordinate 2. Then S is capital S small s L by AE, capital S small s2 L by AE. Okay, so now we already known S1 S2 we already found. So only we need this capital S value, member force due to external loads. So for this, the first thing we should determine the support reaction. So for this we apply equilibrium equation. So from this equilibrium equation we finally determine V is equal to 40, Vd is equal to 40, H is equal to 0. Then draw the free body diagram for each and every joint, then apply equilibrium equation. Finally we determine the member force capital S for each and every member of that structures. That is written in this table. Okay, so this thing is written in this table. So first member 1 minus 50. So in this table we should take tension as positive, compression as negative. Okay, so write all the member force for all the members. Then finally determine this value, capital S S1 L by AE, then finally capital S S2 L by AE. Then finally take a summation delta 1 L. So deflection along coordinate 1 is equal to summation of capital S S1 L by AE, so which is equal to minus 283 by AE. Then delta 2 L is equal to summation S S2 L by AE, which is equal to minus 270 by AE. Then final equation on redundant is equal to flexibility matrix inverse into deflection. Okay, that is delta minus delta L, delta minus delta L. So delta is the total displacement at the joint, delta 1L is the displacement induced in the coordinates due to external loads only. Substitute value. So first redundant is R1 is F10 member force, R2 is equal to HD. Then flexibility matrix we already know, substitute that. Then delta 1 is equal to delta 1L we already know 283 by AE, delta 2L is 270 by AE, minus into minus plus, that is finally 270 by AE. Now multiply this flexibility and deflection, finally it gives F10 is equal to 13.98, HD is equal to 270.72. So now we determine the redundant values. Then with the help of this redundant, so first we determine the external support reaction, other three support reactions, then finally we should determine the